Okay, I'll share some resources for you guys so we can set up the workshop environment. Okay, still waiting for people, I guess. I'll just write things in chat so I know people that join later, I have access to everything. So I'm assuming you guys are familiar with Python, and the instructions are for Ubuntu. If you use something else, I don't know, right here if you need help, or Google or something like that. I'll wait for, I don't know, 10, 15 minutes maybe. Just let me know if you have any trouble. Hello, Razvan. Can you hear me? Can you?
Yeah.
You have audio enabled now, I think.
Yes. How are you, Andrei?
But I can't hear anything from you. Are you talking now?
Talking. I am talking.
Well, this is interesting.
Okay.
It seems I have no audio incoming.
Oh, well.
Well, it's going to be fun.
Maybe you should ask...
Razvan, if you're talking, I can't hear anything you're saying. And I would normally, I don't know, restart my computer, ask someone else to use audio to check for later. Okay. I think Amalia entered. Oh, we are hearing Razvan. Okay, so it's a problem only with my system. Good. That's great. I have audio outside of this window, but I have no audio for this window. Maybe it's a setting someplace. I don't know. Let me see. Oh, Razvan, I can see you. Say something now.
Something else.
Okay, awesome. I can see and hear you. Hello, how are you?
Hello, Andrei. Good. How have you been?
Oh, good. You know, busy, working, stuff like that. Nothing special.
Good for you, man. Keeping busy with those hard AI projects.
Not that many hard AI projects. A lot of hard backend projects, non-AI.
Okay.
Video and sockets and, I don't know, complex systems by their many components.
Sounds good, man. Sounds good.
Yep. Not complaining. How about you?
I've been doing a couple of high-tech AI projects for the past 7 months. One, it's about using satellite data to detect deforestation, illegal deforestation in Romania.
What's it called? Forest Guardian?
Digital Dryads.
Okay. I haven't heard of that one. Heard of another one? Cool. That's a challenging problem.
Yes, it is. And we actually won first prize at the European Commission contest and publications office.
Okay.
And now we're launching a second project also in the area of detecting illegal wood transport. So we're going to put smart AI cameras in the forest, actually, when they leave the forest, and we can detect the amount of wood they are carrying out of the forest. And then we correlate that with legal permits.
Oh, that's cool. That sounds awesome.
Yes.
Looking forward to hearing it being used throughout Romania, at least, or other countries.
Yes.
So good luck.
Romania has bigger problems than other countries.
Yeah. Okay, so I see many people have joined. I've shared a link earlier. I'll share it again. You have to download that link, the file at that link. It's an archive. Unzip it somewhere, and then set things up according to the README. The README is especially written for Ubuntu because that's what I use. If you use something else, the steps may vary. Let me know if you have problems, or let me know if everything works so we can move forward. So I'm expecting you guys to also write some code as I move through this workshop. So it's interactive. Răzvan, how's it going? Did you download it?
Yes, I'm looking at your README. Very short.
Well,
we're gonna use scikit-learn, NumPy, some XGBoost, and Jupyter. Good.
Yes, that's all.
Good. I'm activating my environment now on Windows.
Okay. On Windows, how are you installing it? Do you use Anaconda or something else?
Yes, Anaconda, and I recommend Anaconda for Windows. Yes.
Okay. I've just heard of it. I don't recommend Windows, period.
Me neither. I don't recommend Windows, but if you have to be on Windows, use Anaconda.
Yeah. Okay. So the rest of the participants, how are you progressing with this? Can you please write if you have any issues or if you're completed the steps? Just let me know.
Quick question, Andrei. Can we run all the cells, or do we have to?
No. Well, currently some cells are incomplete. They're missing the code that you will be writing.
I get it. I just wanted to see if everything works on Windows so I could give you an update.
You can just run the first cell, which is doing the import. If that works, then you're good. Because everything else is trivial. As long as you can import XGBoost, which is the main culprit, then you're good.
Okay, so it works for me. Should I paste the install instructions? They're just 2 lines of code for Windows Anaconda. So you have Anaconda installed. I created an environment called Andrei, and this is how you do it. So you create an environment called Andrei, and then you need to activate it. And you say source activate Andrei. And then you don't actually need to put in the Python or NumPy, because NumPy is always included in scikit-learn. And Python you'll get the latest one. And considering most constraints, I would recommend you put them in this order. So scikit-learn, XGBoost, and Jupyter. And then inside the folder that Andrei has given you, you just say Jupyter Notebook. And keep in mind, you have to be in an activated environment. So it will have Andrei in front. And you're good to go.
And ideally, you should have dual screens. I'm guessing a lot of people don't, but it definitely helps. So you can have the exercises on one screen and the slides, this window on the other screen. But if you don't, just switch between the tabs on your browser, and that should be fine. And when you hit enter after Jupyter Notebook, your browser should open the Jupyter Notebook interface, and then there you'll have the, hey, Traian, you're requesting, yes. And after you hit enter after Jupyter Notebook, your browser will open the notebook interface. There you have the notebook with the exercise. Yes. Open it and just run the first cell. Click it and hit Shift Enter. Okay, so how's the progress, everybody? Can I have some status updates? Okay, thank you, Esdras. I hope I'm not mispronouncing it. Anybody else? Are you guys still installing or are you finished? It would really help me to know. I'm in the dark here. The steps shouldn't be too complicated, but it depends on the system you're working and if you've worked with these tools before or not. Well, I think I'll start in a couple. I don't know about Mac. Is anybody here on Mac that can help Alejandro? Okay, if Conda Activate Andrei works, then, and if afterwards you can install everything and run Jupyter Notebook, then that's great. Okay, Alejandro, I see you're good. Marianne, give me an update if you're good. I think we can start. It's gonna be 5-10 minutes until we actually get to the exercise part, so that shouldn't be. There's still a little bit of time left for people to set everything up if they want to. Okay. Well, when we start the exercise, I'll make a little pause there to see if everything's okay. Oh, awesome. Thank you, Ovidio. So my name is Andrei Olariu. I work for StowSoup, and this is a workshop on the problem, the very peculiar specific use case of matching generalists with domain experts. And we'll be using test classification with BERT and gradient boosting trees. And we're going to go from idea to production on this problem. This is a broad outline of the workshop. I'll start with an intro on me and the company. Then I'll describe the problem, the problem the client brought us. We'll go from the business case to the technical challenge. We'll then think about a baseline approach. Then we'll do a cooler machine learning approach because everybody wants machine learning now. I mean, you can't have non-machine learning stuff with the company now because they don't have any buzzwords to add to their description. So you need machine learning. And in the end, we have a discussion on the approach, on evaluating models, and what can we do better, stuff like that. Really hoping for interactivity here. So please type a lot of chat messages. Yes? Okay, thank you. So StowSoup is a digital agency. We build a broad range of, yes, chat messages, please. Thank you, Video. We build a broad range of tools for our clients, mobile, web, and AI. We're usually working with smaller companies that have an idea and they want it implemented. Yes, Razvan.
Sorry, I didn't hear
you.
I'll
try changing slides.
Okay.
Good, and then we'll have decentralization.
Razvan, I'll mute you if possible.
Yes, please do.
Okay, mute for. Okay, thank you. So We work mostly for smaller companies that have an idea and they want to implement it as fast as possible to get to the market or to have an MVP that they can showcase to investors and raise money. And we help them build something fast, build something good, and then we can cooperate in the future, or they can just hire a technical team to take over from us. I've been with the company for, I don't know, 7-8 years or something like that. I'm in charge of AI and machine learning, but I also work a lot of backend stuff, APIs, stuff like that. This is me last year during the pandemic on some mountains in Romania. I have a PhD in natural language processing from the University of Bucharest. And if you know Kaggle.com, it's a platform for machine learning competitions. I have 3 top 10 finishes there while I was doing my PhD because I had some time. It wasn't very challenging. But since then, I don't have a lot of time with work and stuff. So I've neglected it. Okay, great. I don't know anything about my audience. So preparing this workshop was a little challenging. Also, it's not a traditional workshop where I'm in the same room with everybody. So I had to prepare for that, and I had to make some assumptions regarding my audience. And these are broadly my assumptions. I assume you don't have a lot of knowledge of Python, and I assume you don't have a lot of experience with machine learning in general. If you do have experience and you find some of the things trivial, then that means you're a cool, experienced programmer. So just enjoy the workshop, ask challenging questions. I enjoy them. And also feel free to interrupt me and ask questions whenever you feel like it. As I said, lots of chat messages. I want to keep it as interactive as possible to resemble a conventional workshop where there's a lot of communication. And what I want you to have after this workshop is some practical knowledge about the flow of building a machine learning model from scratch. And also the exercises are geared toward that. So I understand that you may not want to do the exercises, you're comfortably sitting behind the computer. But I think you will have a better learning experience if you do the exercises. Okay, this is our client. This is the app we've built. It's called Guided PR. The client came to us and said he is doing the following. Journalists want to write articles. Everybody knows that, okay? And in preparing the articles, they need to interview domain experts. And sometimes the journalist knows domain experts for that particular article, but many times they don't know anybody and they need to search for a domain expert. And there are platforms online that where journalists post their request for comment, and domain experts browse those requests and reply to wherever they feel they can contribute. And our client had the idea of himself doing that matching process, because not a lot of people go on websites and see where they can comment on articles for publication. So the client is doing this matching between journalists that want a domain expert and domain experts. And his monetization idea was of having public people that are interested in more visibility, pay for getting featured in articles. So the domain experts are his members on the platform. Journalists can post requests for free. He's doing the matching. He's telling the journalist about the members that he has that can contribute to his article. And if the journalist accepts to publish them, then the members will pay him a fee. And that's very short the idea he has. And he was already doing it, but he was doing it manually with a database of around 100 members. So a small database of members that he knew personally, all of them, and he was able to do the matching manually between the requests he was getting and the members he had. But he wanted to grow, he wanted to speed things up, and he wanted to automate the whole process. Do you have any questions so far about the business case? Just use the chat here. Anybody? Okay, no questions, I'm guessing. Okay, and this is how a member description looks like. A short intro. There's a lot more information in the back, but this is just the most relevant few phrases that we have on a member. This is Brad. He's a colleague of mine at StoneSoup. As you see, he has a lot of buzzwords because he has to have a lot of buzzwords. This is the field of AI, you know, IT. You need buzzwords everywhere. And this is how a request looks like. So a journalist working at Raconteur Media has submitted this request. He has a deadline. This is very important when you're doing the matching. You have to submit the matches before the deadline. You have a summary, demystifying AI and machine learning in the financial services industry, and then you have some broader description of what he's looking for. So this is how a request looks like. You've seen how a member looks like, and the matching must find for each incoming request the best members to submit to that journalist. Okay, so what do you guys think? This is the interactive part. Just write stuff here, please. Anything? Don't let me talk by myself. What do you think? How can we approach this problem? Any simple idea that you have? Anything, please? Come on, guys, don't let me beg. I'll just keep waiting until I have something. Give Brad even more buzzwords. Model it as a document similarity problem. Okay, we can model it as a document similarity problem, but how do we solve it? I mean, how do you match keywords? Okay, that's a good approach. So Razvan, you said give Brad some more buzzwords. Yeah, but you know, term frequency, inverse document frequency, the more buzzwords you add, the more meaningless they become. So thank you, but we'll move to another idea. We can model it as document similarity, but also there are a lot of ways to approach document similarity. Roland, do you have any ideas how can we approach it? And Alejandro, match keywords. Okay, how do you select the keywords and how do you match them exactly? So what I'm looking now is for a baseline approach, which would be a simple, easy to implement, easy to explain, easy to understand, predictable algorithm that doesn't require any training data. Term frequency, okay. Term frequency, inverse document frequency would be a way to do it. Bag of words, okay. Those are some good ideas that should work. Yes. Of course, if you do bag of words, you know, you remove stop words, or you do term frequency, inverse document frequency, which handles that automatically. What we chose to do here for our baseline is something where we did even less work than that because we're lazy. And also when you have a project that you want to ship as fast as possible, you want to write stuff, use stuff that's already been made by others instead of you writing code. So we just thought of it as a search problem, and we indexed the members inside Solr into Solr, which is a search engine. Just imagine your own Google. Members were the documents inside Solr, and each request coming in was the query. So we send the request as a query to Solr. Yes, they do use term frequency, inference document frequency internally. So they performed pretty well. And Solr returns a list of results ranked. So the first result is the best match according to Solr, the best matching member. And we just cap that list at, let's say, 10 members or whatever we feel, or we just use a threshold. And then we have a moderator to review and correct the matches before sending the matches to the journalist. And that third step is important because we don't trust this approach. I mean, it's simple, it's straightforward, but we don't trust it. We don't know how well it performs. We don't know if the results will be relevant or not. We haven't evaluated it. So we have this manual review step. But also, this third step is important because it allows us to build a manually annotated dataset that we can later use to train a machine learning model on top of evaluating this model. So is the baseline clear? Just let me know if it's or if it's not clear. I'm assuming not everybody is familiar with Solr, but everybody should be familiar with Google, and Solr is just like a very simple open source version of the Google search algorithm. That's an oversimplification, but you know, you get the idea. Okay, and here we have the first lines of code. Marian, have you finished installing your workshop environment? Anybody? Or is anybody here that is still? I just finished. Okay. Because now we have to run this little piece of code that loads our database of matches. So these are the matches that we had after that third step, after the manual review step. And you can run this box, and you'll have all the matches loaded. Then please have a look through them. Try to get a feel of the data that we have and do a very short exploratory analysis on it. If you don't know what exploratory analysis is just you going through the data, getting familiar with it, getting to know it. It's not a complex data set, so it shouldn't take a lot of time. I'm say a few minutes is more than enough. And after it, you should have a good understanding of what of the data you're working with. So I'll wait for a few minutes. Just write in the chat whatever you come up with. Okay. Okay, thank you, Esdras, Gabriel. Yes. So you've reached this step, and you've counted the matches, and you have an example match. We have the member ID for each match and the request ID. So each match is a pair of IDs, and also two flags if it's a mismatch. If it's true, first let's start with the auto-generated flag. So if it's true, this means the match is coming from Solaire. It's an auto-generated match. If it's false, it means the match is coming from the moderator. The moderator saw this member wasn't matched to the request and manually added it. So the moderator added a match that was missing. And if the mismatch flag is true, it means that we have an auto-generated match that was not correct. So the moderator considered it to not be a good match for that request and marked it accordingly. If mismatch is false, then we don't have a mismatch here. You can continue with exploratory analysis for a couple more minutes, see if you find anything else interesting or not. Let me know what you have. Yes, so we have majority are mismatches because the majority of the data is coming from the from Solaire. Obviously, for a moderator, it's not that easy to add other people to the list. So it's more easy for him to say this is not a good match than to add more people. So that's why you have a lot of mismatches here. This is the structure of the data. Okay. Yes. Okay. Esdras and Razvan, thank you for your input. This is good to know. And yes, Gabriel, you found this. I was hoping somebody would find it. I added some fake data in the end to see if people are paying attention. So this is a dummy entry that I've added. You have to remove it manually by running this line. So please, everybody, run this line to remove the last element. Otherwise, code in the future will crash. Because as you see, the member ID and the request ID are not int, they're string. Okay, I'll leave this comment here. Now, moving forward, I'll need you guys to write some code. What we want to do now is, given our data set of matches, we want to build a machine learning data set out of it. And for that, we need a list of the labels we call Y. These are the correct labels. And we need also the baseline predictions that our Solaire algorithm gave us. So you'll have to write some code here. And if all goes well, when you run this box, the asserts will pass. Let me know if you have questions about what you have to do. So you need to generate two lists, Y and baseline predictions, that are the same size as the matches. So for each match, you'll add an element to Y and an element to the baseline predictions list. And Y are the correct labels. So if that item in the matches list is a good match, or it's a bad match. And the baseline predictions are if Solaire said that's a match, or if Solaire said that's not a match. So you can find that out using the mismatch, with using the auto-generated flag and the mismatch flag. You can compute both of these arrays. So you have a couple of minutes to work on this. Let me know if you have questions. If you finished writing the code, please let me know. If you have troubles, please let me know. And there's no scenario where you don't let me know, okay? Oh, the template text. You don't have to copy this. You have the exercise notebook where you have this code already written, and you just have to fill in below the comment. So all of this code is in the exercise notebook. Sure. Let's move backwards a little. So we have the member ID, which is the ID of the member, and the request ID, which is the ID of request. You don't have to deal with them now. Only that you need to know is the mismatch and the auto-generated fields. If auto-generated is true, this means this match is coming from Solaire. It's not a manual match, it's an auto-generated match coming from Solaire. If mismatch is true, this means we're looking at an auto-generated match that the moderator marked as not a good match. So it's coming from Solaire, but it's not a good match, it's a bad match. If auto-generated is false, then obviously mismatch is also false because the moderator will not add a match and then say his match is not false, he's not good. So whenever we have auto-generated false, it means the match is coming from the moderator and it's a good match. When auto-generated is true, the match is coming from Solaire and it can be a good or a bad match. So when generating these two data sets, you have to look at the two flags and treat their combination accordingly to add to Y and baseline predictions. In Y, we're interested if the match is correct or not. So if it's a mismatch, it means it's not a good match. In baseline predictions, we're interested in if Solaire said that is a good match or not. If it's added by Solaire, but if it's added by Solaire, it means it's predicted as a match by Solaire. If it's added manually, it's not predicted as a match by Solaire. Hopefully that made sense. If it doesn't make sense, just let me know. Well, it's a little too late for that, Razvan, I'm sorry. But yes, I'll keep in mind for the next time I present this workshop, which is probably never. So this is a unique moment in history. But nobody, I mean, I've presented this to a few people. Nobody has complained about this. So I'm guessing they're not that bad of names. They're not the worst names in the world. But you're talking about Y and baseline predictions, right? Oh, Y is the default name for the correct labels in general in machine learning. So, and baseline predictions, this is the baseline. So those are the predictions for the baseline. So yeah. If you're talking about mismatch and auto-generated, well, they're named based on what they represent. If it's auto-generated or manual generated, that's a flag. And if it's a mismatch or not. This is also how the mismatch is presented in the visual interface, in the moderator interface. So that was intuitive for us at the time. So these are historical names. Okay, I hope you guys have written code. Did you guys finish writing the code for this? Okay, then I'll move forward. I'll also share the correct code, so I don't want people left behind, or maybe if you haven't figured out what needs to be done, it's going to be obvious. So here is how the code looks like, at least my implementation, which is a very explicit one, because in Python you can write things in in just a few lines. So for each match, I look at both flags. And if it's auto-generated, I add 1 to the baseline predictions. If it's not auto-generated, I add 0 to the baseline predictions. And then I look at the mismatch flag. If it's auto-generated and it's a mismatch, then I add 0 because this is not a good match. If it's auto-generated and not a mismatch, I add 1 here because it's a good match. Then if it's not auto-generated, we can have a mismatch that is manually added. So we in the other case, we just add 1 here. And this should be it. I'll just copy paste this here for whoever was not able to finish this. So you have the code. Okay, that looks horrible. I'm sorry, but I don't have what can I do to format this? You just have to format it. I think this system cut out the new line characters. So is everything clear here? Are there any questions? Please, yes or no would be perfect. No questions. Awesome. Now, we'll move forward and do a little analysis. We want to know how good is this baseline prediction. So we convert both lists to NumPy arrays. So we can do a very easy one-liner to get the accuracy of this model. And we see that we have an accuracy of 34%. So here we're checking the number of matches where baseline prediction agrees with the correct values. And we do a sum, divide by the length of y, and we have a 34% accuracy. Do you have any questions about this number? The way we computed it? Yes or no? No? Yes? No. Okay. Do you think it's a good or bad score? Or what would you say if you have an algorithm that gives you 34%? Anything? Well, it would be bad if you're doing pedestrian detection for autonomous driving. This would be bad if you can't see the pedestrian in 34% of the if you can only see the pedestrian in 34% of the cases. That's bad if you're doing autonomous driving. But imagine you're doing Google searches, and you have an algorithm behind the Google search, and 10 of the first 10 results on the page are what you are looking for, and the other 7 results are bad. Would a page with 10 results, with 3 results out of 10, 3 good results, would that be good or bad? If you frame the problem like that, you would say it's good. I mean, you got 3 results that you were looking for. Yeah, it seems better. So it depends on the perspective. In our case, I would say don't judge by the number. Just ask for feedback from the moderators, because they are the ones that interact with this system, and they are the ones that feel if the system is bad or not. Nobody else sees that. They're the manual review step, and they should know if the results are good or bad. But other than that, this is just a number that we can use to evaluate, changes in improvements in the model, or just compare it to another model. But apart from that, we can't say anything about if it's good or bad. Okay, so we had a short intro on the baseline. Let's now start with thinking about a better solution. And we'll start with a little bit of context on the theory of the solution that I'm proposing. And I'll start with Word2Vec. I don't know if you're familiar with Word2Vec. It's been around since 2013 or something like that. It's a technique for computing word embeddings. So you have a word and you want to convert that word to an array of floats such that you can compare words based on those arrays. And what happens as a very fast intro in Word2Vec, there's a neural network that is being fed a lot of phrases, a lot of sequences of words from a very large data set. And those arrays that the neural network computes, they have some interesting properties, and they show some interesting relationships between words. The arrays, I think, are something like 128 dimensions. So you have a word is converted into a list of 128 floats. But if you do a dimensionality reduction to 2 dimensions, then you can plot those lists in a chart, in a scatter plot like here, and then you can see similarities between words, which is cool. It's not particularly useful, but it's cool. Everybody likes a cool chart. I can add it to a slideshow. Yeah, and but Word2Vec wasn't famous for this. It became famous for the relationships between words, between pairs of words. For example, they're famous for that. If you have the embedding for king, you subtract the embedding for man, and you add the embedding for woman, you'll get an array that is very similar to the embedding for queen. And that's very interesting because you can combine arrays in this sort of way. And you have these relationships that are not just king, queen, but also tenses of words, and also countries, capitals, and the list can go on. These are just some of the relationships that were explored, but each word has 128 dimensions, and who knows what relationships are being found there. So this was again interesting. A lot of articles were written on Word2Vec, and there were a lot of interesting applications of it, but it wasn't a breakthrough compared to what was happening at the time with neural networks on images. There we had pre-trained neural networks that were being used everywhere, trained on the ImageNet dataset, and then just fine-tuned for whatever whatever problem you had, and deploy it there. And Traian, yes, definitely helpful. But let's go a step forward in what's even more helpful, and we're going to 2018, where we have the appearance of BERT and other sentence embedding algorithms. So we're no longer working with word embeddings. We are now working with sentence embeddings, and we have models that were trained on, yes, transformers, yes. So we have now models that are trained on huge data sets. Then the models are trained, and you can use them out of the box for your problem, or fine-tune them on a small data set. And when they appeared they represented a breakthrough in NLP, similar to what ImageNet and pre-trained convolutional neural networks represented for images. And they brought significant improvements on most problems in the field of NLP. And for this project, we used BERT, which is developed by Google. It's not a requirement for today. You didn't install it. Installing it is on Ubuntu something like this. It comes in two parts. You have the server, which you start standalone. It loads all the pre-trained network in memory, and then it's just waiting for requests. And then you have the client, which you embed in your code, use it there, and the client will send requests to the server for embedding some text, and the server will respond. And this is how it was written, at least in Python. The code looks something like this. You import the client, you send some sentences, and the result, for each sentence, you have an array of 768 floats. But there's also larger networks that have a little over 1,000 floats if you want a stronger model, but also a model that takes longer to compute and also uses more RAM memory. And let's see the results for these three sentences. With what we did there is multiply all of the three sentences pairwise, and we see multiplication on these embeddings is some sort of similarity, because each float is between -1 and 1. 1 means on that dimension there's a strong value. Yes, something like cosine similarity, or the dot product of vectors. Yes, because we're talking about vectors here. So if you have 1, it's strong in that dimension. If you have -1, it's very weak in that dimension. And if you have 0, it's something that's not opposed but also not strong. And you can multiply them and see if two vectors are similar or not. And for this problem, I can't share the data set of member descriptions and request descriptions because that's not possible. But what I could share is the list of member embeddings and request embeddings. Hopefully, there's no way to reverse engineer that. So you can just run this box in your exercise notebook, and you'll have loaded all of the member embeddings and the request embeddings. You'll have two dictionaries here. Let me know if you finished this or if you have questions regarding the embeddings. Yes. So here the first and second sentences have a larger similarity value or dot product compared to the other two pairs. And you can see lion is the king of the jungle, the tiger hunts in the forest, and everybody loves New York. This is a very simple example. Yeah, then the first and the third, or the second and the third, because you have three products here. And this is, we will also be using that product later on in our model as a similarity of embeddings. So let me know if you've loaded this or if you have problems loading the data. All the data should be in the archive I sent in the beginning. Awesome. Thank you, Ovidio. And now that we have a training data set, this is where you build a training data set. We already have the baseline predictions and the Y labels. We need to build the X array, which is actually a matrix of the data that we're working with. And I've already written this code. You have it in the notebooks. For each match in our list, we add a new line to X, which is the dot product between the member embedding for that member ID and the request embedding for that request ID. So we have X. We then convert it to NumPy array. And then we apply the train test split from scikit-learn. This train test split will split a data set into two parts, one for training and one for testing. And we pass X, we pass Y, the true labels, we will pass the baseline predictions, and we say we want a test size of 5%. Okay, goodbye, Razvan. So we have a test size of 5%. And then we can plug this into an algorithm and get some results. This is the shape of X. So we started with almost 40,000 matches. We subtract 5% here, so we have 47,000 training examples and almost 2,000 test examples. So this is the data set that we've converted from text form to a numerical form, which is very good because it's easier to work with numerical data than with text data. Now we need an algorithm to help us separate good matches from bad matches on this data set. And we'll start from a decision tree. This is an example of a decision tree trained on the Titanic data set. You can find this data set online, such as on Kaggle. According to this data set, if you were female, you had a good chance of surviving, 73%, or if you were a kid with fewer than 3 siblings, you had almost 90% chance of surviving the Titanic shipwreck. But if you were a grown-up man, your chances didn't look very good. I'm sorry. So this is a simple decision tree. At each step, the decision tree will select the most discriminant feature in the data set, in the training data set that it sees, and do a split on that discriminative feature. It starts with the gender, and then it continues with the age, and then it continues with the number of siblings until a node does not have any more relevant discriminative features to split on. These are parameters for the decision tree generation, because you can go further to build a more complex decision tree, but that will be prone to overfitting, or you can go more shallow to a simpler decision tree, but that might not have enough power to model the data accordingly. So from decision tree, we move up in complexity to a random forest. A random forest is a set of decision trees, each individual tree being trained on a subset of the data, on a random subset. So this is like 50% of the data. This is another subset of the data, and so on. Each tree, after training, when it sees the test data, will make a prediction on that data, and we do a majority voting with the predictions to select the final class, which is the prediction of the entire random forest. Questions up to now? Let me know. Does it make sense? Or you might not be familiar you might already be familiar with this concept. Okay, thank you, Esdras. You have no questions. Anybody else? Well, if you do have questions, just feel free to write them there. We can stop at any time. There's no problem. So this is a random forest. It's cute, but just let's go a step further in complexity with the gradient boosting technique. Gradient boosting is something like this. We have a decision tree that predicts the training data, and it will make some matches. It will make some errors. For each of the errors, we see the errors here. It's splitting based on this line, and you have 2 blue dots that are in the red section and 1 red dot in the blue section. And these are the errors that the first tree made. We for these errors, we assign higher weights, and then we train a new decision tree with the higher rates, and we see this tree will generate another split, and this tree will also make some errors, and we give higher weights to these errors, and we repeat. We train a new tree and increase the weights for the mistakes it makes, and so on, until we have our predetermined number of trees, in this case t, and then the combination of predictions becomes the final predictions for the whole model, the whole ensemble of models. Questions here? Don't worry about these charts. Nothing to worry about. Just if you understand the idea of boosting the weights on errors so that we can get a better prediction in general. So these are called now gradient boosting trees, and in general they outperform random forests. And this is what we'll be using today. Let's go to see some code. We'll be using XG. How the different outputs are combined? There are several ways of combining them. I think it's also something that depends on the implementation of the tree, but you can, a very simple way would be just to do majority voting. So you add all of the predictions, and the prediction that is most common will be the output, if we're talking about classification. If we're talking about regression, you can just do an average. This is a simple answer. There are more complex answers, but we're not going to go about over them because this is besides the point. I just wanted to present a broad overview. There are many differences, many techniques to optimize random forests besides gradient boosting. And there are several ways to combine predictions, but just imagine you're doing an average or a max or something like that on the outputs to select the best, the best and the final result. Does that answer your question? Okay, thank you. And we're now using XGBoost. We're using the XGBoost classifier. We already installed scikit-learn, and scikit-learn has implementations for random forests, for decision tree, for gradient boosted trees. XGBoost only implements gradient boosting trees, but it's a superior implementation in terms of performance. So we have stronger models when using XGBoost. And now we'll initialize the classifier. In my code here, I'm using 300 estimators, but I'm also training on my GPU. The code you have is, I think, with 5 estimators. Correct me if I'm wrong. I don't have the notebook you got in front of me now, but I think it's only got 5 estimators, and the GPU part, which is these 2 lines, they are disabled because I'm assuming you don't have a GPU set up with CUDA so that Python can work with it. because the setup process is not trivial, unfortunately, at least on my machine. Obviously, with 300 estimators, you would get a far better result than with 5 estimators. The number of estimators is this T here. So you would have 5 decision trees, whereas I would have 300 decision trees. The depth is how far down should we go splitting the tree. And given we have a data set that has 700 dimensions, you can go pretty far here without worrying about overfitting. But the further you go, the more the model will overfit. And the other parameters are nothing to worry about. And now we're fitting the model on the training data, which is 95% of the whole data set, and then making predictions on the test data, the remaining 5%, about 2,000 examples. You have this code. You can now run it. Let me know if you've run it. It shouldn't take a lot. It should take in the matter of 10 seconds or something like that, depending on your CPU, because this will run on a CPU in your configuration. If you feel you can wait a little further, you can bump up the number of estimators and run again with 10, 20, 30, whatever you feel. So just let me know when you've finished running this code. Okay. Anybody else? Should I wait or should I go forward? Okay. Let's then go forward. Now, I have the baseline predictions. These are 5% of the original baseline predictions we computed in the beginning. They were split using that train test split function from scikit-learn. And then I'm computing the baseline score again on just this subset of the data. And I'm also computing the accuracy of our new model. And here I got 34%. You should have the exact number. And this is the score I got with 300 trees. What scores did you get here? You should have something smaller if you only ran with those 5 trees. Okay, 69% sounds about right. Okay, awesome. So if you feel like waiting, you can try with a larger number now or later, whatever you want. But that's about it. So how do you feel? Did we get a good score now? Anything? This should be the interactive part about discussing the results and stuff like that. Yeah, it's better, right? Yeah. Do you think the job is done? We should go home and feel happy about it? Yes. You feel yeah. Regarding doing better, these scores are not correct, honestly. It's a huge improvement, but this just outlines what happens when you don't think thoroughly about the problem you're trying to solve, and when you just leave metrics to guide you, and the metrics are flawed. Let's talk about this for a little. We're using accuracy here, which is, you know, it's nice. Accuracy is a widely used metric for evaluating machine learning models. And this is the formula for accuracy. You have the number of the number of correct predictions divided by the total number of predictions. And this is accuracy in the general multi-class problem. But we have a binary classification problem, right? So you have only 2 classes, and there's a better formula for the 2-class accuracy. It's a equivalent formula. Marian, I'll get back to F1 shortly. I mean, F1 also uses the confusion matrix. It's not necessarily using the F1 score or the accuracy score. So this is accuracy for binary classification problem using the confusion matrix, and you have the true positives, false negatives, and true negatives. Are you guys familiar with the confusion matrix? I mean, do you know what it is, or are you just starting with machine learning and this is a new concept? Because I don't know if I should go into more details here or not. Okay. Anybody else? If you don't understand, this is your time to say. Okay, so we have the confusion matrix, and accuracy is computed as the number of true positive plus the number of true negatives divided by all of the values here. True positives is when my model predicted a positive outcome. It predicted it's a match, and it was actually a match. And true negatives is the same, the other element on the diagonal, the main diagonal, when the model predicted it's not a match, and it's actually not a match. Like this is rephrasing it. Do you see something weird here? So the model predicted it's not a match, and it's not a match. Are we missing something? Anybody? What are we missing? Do we have any true negatives in our data set? No, we have no true negatives. So the way we computed, the way we built our data set by design doesn't have the true negatives. So we're using accuracy, but we're using accuracy on a partial data set. So the numbers we got, they show the baseline is performing very bad in the beginning, but that's a number where we don't add the true negatives here and here. So it's not a real value for that model. Just to explain it in an easier way, if we have 100 members in the dataset and the algorithm Soler returns 5 matches, then the moderator will say, okay, these are good matches, but I'll also add 5 other members to the results. That means the remaining 90 members in the dataset, in the database, the ones that weren't selected by Soler and the ones that weren't selected by the moderator, they are the true negatives. But they are not in our matches dataset, and we're not adding them. So we have 90 members that Soler accurately said they're not matches that are not here. So our dataset is missing this very important subset of data. And we need to correct it to add true negatives to our dataset. First, to better understand our algorithm's performance, and also to train a better machine learning model. And this is what we're going to do in the next slide. You have this code here. You have to complete between these 2 comments, add some code. I was thinking of adding 3 times the data we have already. So we have almost 40,000 matches. Let's add 120,000 matches to them in this list. And the list should be a list of dictionaries with this format. And what we want here is to have pairs of member ID and request ID. Member ID being one of the IDs of members, request ID obviously an ID of a request, such that in our current matches data set, this pair of member ID and request ID doesn't appear already, because that would be an invalid row. So we want pairs of member ID and request ID that are not in our current matches list added here without anything repeating itself, stuff like that. I've added some tests which are a little expensive. So is it clear what I am expecting here? What you should be doing? This is your time for questions or time for coding. This might take a little. I think yes, I want synthetic data, yes. But it's not synthetic in the literal case, because we know all of the pairs of member ID and request ID that we don't have in the matches data set, they were not matched by Solaire. So Solaire said, these are not good matches. And also the moderator didn't add them to the list of matches. So we know they are not good matches. So yes, just add randomly pairs of member ID and request ID such that they're unique and they're not found in the existing data set. And we know about them that they are not good matches because Solaire didn't provide them in the beginning. Is it clear now? Okay, I think I'll let you guys for 10-15 minutes. If your code is good, these asserts should pass. Let me know if you have any questions. This shouldn't be complicated if you're familiar with Python. Otherwise, I guess it's a good time to get familiar with Python. So good luck. Let me know if you have questions. So did anybody finish? Anybody? Okay. Damn it, this without the new lines, that's very hard to read. Okay, I'll share the code that I have. Whoa, this is a lot of code. Okay, so this is the part that I added here. Okay. So what I'm doing, I'm importing random. I have a list of all the member IDs and the request IDs, and also I have a set of the matches. And each item in the set is a tuple with the member ID and the request ID. And I do a while true, randomly select the member ID and the request ID. I see if we already have a match for this pair. And if we have a match, then I skip and try again. Otherwise, I add it to the true negatives. I add it also to the all matches set. And if I've reached the count, I break. And this is it. Does it make sense? Yes, no? Yes, makes sense. Awesome. Okay, I'll share it here, but as you saw, you won't get any new lines. I'm sorry about that. I can't even share it here. I'm sorry. It's just too big of a text. Okay, I'll share it in pieces. Oh, yeah. Okay, gist. Sounds good. Thanks. One moment. Okay, so you have the gist here. Let me know if you can access it. Yes, you should be able to access it. Good. So this is the code. We have a larger data set now that we need to generate. We have the new matches, but we need to generate the X true negatives, the Y true negatives, and the baseline predictions for these true negatives. But this is straightforward. I'll skip through this because it's not complicated. It looks like this. For each match in these true negatives, I add to xtn the dot product between the two embeddings, the one for the member and the one for the request. I add to y true negatives a 0 because this is not a correct match. And to the baseline predictions true negative, I add a 0 because Soler said this is not a good match. So both arrays, X, Y, and base predictions for these true negatives will only have zeros. I'll also add a gist with this. One moment. Added a gist here. Now, so that we can spend a little more time discussing the results. Nothing complicated here. We're using the vstack and hstack functions from NumPy. Vstack for x because x is bidimensional, and hstack for y because y is a simple array. And here we are splitting the new data set into train and test. We're doing this so that we keep the test data set in our original data set, which is X test, Y test, so that we can compare the original model, which was only trained on X trained and Y trained, with the new model that will be training on X train extended and Y train extended. And then we can correctly also compare the predictions of our first model. The purpose of all of this code is to be able to accurately compare the first and the second models without having to retrain the first model. The first model was already retrained on the original train data set and was also tested on the original test data set. And we don't want to reshuffle the data sets, the test and train, because that will invalidate the original model. If we shuffle the data set and then test the originally trained model, many of the test items will have been originally in the train part and would have been seen by the original model. Does that make sense? Yes, no, maybe not. Makes sense. Okay, so it's important. You need to spend time to correctly compare. Yes, you need to spend time to correctly compare models, old models and new models, without having some sort of data pollution. When you're using training data to test the model, because the results will be incorrect. So you want to test the model all of the time on data it didn't see in the past. And this is the purpose of this code, which I'm going to share in another gist. Okay, this is the gist with these few lines of code that you can copy into the notebook. The certs should pass. And now we're training a second model. Again, you'll have 5 estimators here, and everything here should be the same. Run this code. You should run on the new data set. Let me know what you have. Okay, that's great. 0.89 is a pretty good result, and you're also re-evaluating your original model. So remember, originally on the old data set without true negatives, we had 34% for the baseline, and I had 81, I think. You guys had 69. And now we can see the original model is worse than the baseline. Previously, it was scoring a lot better. Now it's scoring worse. But the newer model, which was also trained on the true negatives, is performing better because it's seeing more data. It has a better understanding of what it's doing. And these are results that we can now trust. Does it make sense up to now? Okay, awesome. Hopefully you're also getting results around ballpark like this, maybe minus 5–10% for each of these two numbers because you have fewer trees. This is what I got with 300 trees, and running on the GPU took tens of seconds or something like that. So a GPU is 10 times faster than a CPU on problems like this. So here we're using accuracy. Since we've approached this problem like as a classification problem, and we're working with classification models. But this, we approached it as a classification problem, but it's not really a classification problem, is it? It's more of a ranking problem. We have all the members. We want to find the best matching members, so it's a ranking problem. When we say classification, we say, is this member good for this request? And we repeat the question for each member in the database. But for ranking, we see all the members and we say, which are the best members for this request? And give me a sorted list. Why does it matter? When working with accuracy, each training model has a threshold, internally has a threshold that separates what is good from what is bad, what is a 1 compared to what is a 0. And usually that threshold is 0.5, but it's something that you can tune. But when you're doing ranking, there is no such threshold. Instead items have a score assigned to them, and they are then ranked by that score. Imagine a 0.8 means a very good match, but also a 0.2. If the highest score is 0.2, then that is a best match. Yes, top X, you can do a top X with ranking. I think top X is also translated in a ranking problem. This chart here is the ROC curve. Not going to go into the theoretical discussion about what it is, because I don't think I would do a good job at it. But I'll talk about how to interpret it visually. The blue line is a worthless model because a coin toss would give you this line. A coin toss, when you say, is this a good match, and you flip a coin, and the ROC curve for that algorithm would be this diagonal line. The red line is a better model, and this green line is a very good model. And the perfect model would be something that goes around the corners of the graph to the upper left side. Not going into the theory behind this, because that's beside the point. This is the ROC curve, and the metric we'll be using is based on the ROC curve, and it's computing the area beneath the curve or area under curve, and that's why the metric is called AUC, area under curve. And That's exactly what it measures. The worthless algorithm gets 0.5. The perfect algorithm gets 1. Let's see how that looks like. We import it from sklearn. We have, let's say we have the true predictions y and the true labels y, and the model's predictions all are 0. But we have an element that is 1. When we are comparing accuracy, accuracy says we have an algorithm that scores 0.9. Wow, this is great. But then we look here, and this is worthless. But AUC will say this is 0.5, so it's worthless. So it's a better metric. You can say F1 score, the F score might be a good, but AUC is better than that also. Imagine a COVID test. If that works 99%, but if you test it only on 100 people and only one has the virus, and the accuracy, the COVID test always says it's you don't have the virus. If you test it on 100 people and only one has the virus, the accuracy will be 99%, but the AUC would be 0.5, so it will you will see that it's a worthless test. So this is what we're going to use. Let's also see how we can use this when we have float predictions. Instead of having 0 and 1, we can have a number here between 0 and 1. And AUC also works for that. So in this case, we have these small numbers, but we see we have 0.2, which is the largest number here, and corresponds with the true positive. And in this case, we have a perfect prediction because it's correctly ranking all of these elements. Does it make sense now? So in short, these are the differences between AUC and accuracy in terms of why AUC is better. And what we want to do now is reevaluate our model using AUC, and we see the scores shift a little, but the order of the algorithm is the same. Of the scores is the same. But now these are scores that we have more trust in because they are scores based on a metric that is specifically for such a problem. We are doing ranking, and AUC is a good metric for ranking. Whereas accuracy, you can say you use accuracy here. Oh, Video, you're asking why is the baseline better than model V2? For the model, okay, because the baseline was already pretty good. So model V2, when you trained it on with only a few trees, it didn't get a very good score. When we added those true negatives, they really boosted the score for baseline. I don't know how these would feel in practice, comparing the baseline with V2 model trained on just a few trees, but I would say they would feel pretty similar. So it's not an easy problem for machine learning, and that's why we struggle to find a good algorithm here. But when you see we boost from 5 to 300 trees, the relative error in reduction, the relative error reduction here is significant. We're cutting the error by 40%, which is a huge reduction in error. From 83 to 90, you can say it's in absolute terms a 7% decrease, but in relative terms it's a 40% decrease, which is significant. But yeah, you have to train a lot of trees for that. But you also have to consider the data set is pretty complex. And we're finishing our time now. This would be the final discussion that we don't have a lot of time for. what can I say? The model has been in production for 2 years. There were some questions in the beginning as to why someone was matched or someone wasn't matched. Usually you can just figure that out from the text. You just look at the member, you look at the request, and you see there are some words in common there, and you figure out what's happening. And a year ago, the manual review step was removed. So matches now are being sent directly to the members, and the members are being asked to comment on the request. So there's no human review in place. So that means the members that were doing the review were pleased with the algorithm, and they thought the manual review was no longer needed. And we haven't had any complaints since then. We can talk about what we can improve. What can I say? You can replace the gradient boosting model with a neural network, a fully connected neural network. Instead of just doing the dot product of those two embeddings, you can also, besides the dot product, you can also add both embeddings as features, plus the absolute difference between the embeddings. And this is what a similar approach from Facebook is doing. They're using all of these features, they're pushing them into a fully connected neural network to assess the similarity between sentences or between texts. These are some improvements. I don't know, if you have other ideas, you can write here. If you have questions, you can write here. I will share the code, the entire slides and everything on my GitHub Plus blog later today or tomorrow. This is the link. Okay, I'll share it like this. Okay, so I'll share my code here, a repo with the slides, the data, everything. Also my notes, because I have some notes that you didn't see but have helped me remember my thoughts during this presentation, during this workshop. If you have any feedback, just let me know, questions, now would be the time. Or you can just take a break. I know there are some other workshops starting in 30 minutes. Anyway, it was nice having you today. Thank you, Esdras, and thank you everybody else, especially the guys that have commented, because it's kind of weird hosting a workshop with a virtual audience. It's very different to hosting it live, face-to-face. It kind of cuts the feedback loop. Thank you, Alejandro. Thank you, Ovidio. Okay, I guess that's it. I'll be available here for a few more minutes. If you have questions, just write them. Thank you, Marianne. Okay, nice having you guys. Goodbye.